Today we will discuss some numerical problems on Bragg's law. In the previous video, we had discussed derivation of Bragg's law, which is n into lambda is equal to 2 into d into sine theta, where n, an integer, is called the order of reflection. Lambda is the wavelength of X-ray used in the diffraction experiment. D is the interplanar spacing, that is the distance between two planes which are having the same Miller indices HKL. Okay, and theta is the Bragg's angle, that is the angle corresponding to maximum reflection. So based on this equation, let us solve one or two problems. So I have copied down the problem here. So let me read the problem. A beam of X-rays of wavelength 0.154 nanometer produces a first order reflection at 5.5 degree from 100 planes. Calculate the distance between the successive planes in the crystal. Okay, so here we have to find out d, the distance between the planes which are reflecting the X-rays. Okay, that is distance between 100 plane. While solving any numerical problem, first and foremost thing you have to do is write down the values that are given in the problem. Okay, whether those values are required or not, it is always better to write down all the given values. Okay, so they have mentioned that it is a first order reflection, so n is equal to 1, and they have also mentioned that reflection takes first order reflection occurs at 5.5 degree, which is nothing but the Bragg's angle theta. So theta is equal to 5.5 degree, and also they have given the value of lambda, that is the wavelength of X-ray used in the experiment. So three values are written here. Lambda is equal to 0.154 meter. Our aim is to find out distance d. Okay, to find out d, we have to use Bragg's law, which is n lambda is equal to 2d sine theta. Here we have Bragg's law, n lambda is equal to 2d sine theta. What we are supposed to find here? We are supposed to find d. So let us rearrange the equation. D is equal to n into lambda divided by 2 into sine theta. Okay, since all the values are known here, okay, let us substitute 1, that is n, into lambda. Remember, lambda is given in nanometer, which has to be converted to meter. So 0.154 into 10 to the power minus 9 meters. Remember, 1 nanometer is 10 to the power minus 9 meter. Okay, divided by 2 into sine theta, that is sine 5.5 degree. Okay, you have to use the scientific calculator. The value of sine 5.5 is 0.0958. So if you calculate, the answer is 0.804 into 10 to the power minus 9 meter. Okay, you can convert again 10 to the power minus 9 meter into nanometer. Okay, so the answer is 0.804 nanometer. So the distance between the two 100 planes from which the X-rays are reflected, producing a bright spot at 5.5 degree, is 0.804 nanometer. A straightforward problem based on the equation n lambda is equal to 2d sine theta. Let us solve one problem, a similar problem, which is calculate the angle at which A, first order, and B, second order reflection occurs in an X-ray spectrometer when X-rays of wavelength 0.154 nanometer are diffracted by the atoms of 111 planes, okay, of a crystal of interplanar dimensions 0.415 nanometer. Okay, what is 111? It is nothing but the HKL values of the plane, Miller indices of the plane. Here we have to get familiarized with this word X-ray spectrometer or X-ray diffractometer. It is the instrument in which we carry out X-ray diffraction experiment and obtain the diffraction spot. What does an X-ray spectrometer contain? How does it function? Will be discussed in the next video. So just remember this point, uh, that X-ray spectrometer is nothing but name of the instrument. Some certain values are given. You have to find out the angle theta, Bragg's angle theta, at which first order reflection takes place and second order reflection takes place. So I have listed down the given values. Okay, I have divided this into two parts. This is A, question A, and this is question B, and I have mentioned the values. For question A, it is a first order reflection, therefore n is equal to 1, and for the second part, second order reflection, n is equal to 2. Remaining things are same for both part A and part B. They are wavelength of X-ray lambda 0.154 nanometer, and the distance between 111 plane is given. It is 0.1415 nanometer. What you are supposed to find out? You are supposed to find out theta, that is Bragg's angle, for the first order reflection, that is when n is equal to 1, and the Bragg's angle theta for the second order reflection, that is when n is equal to 2. The solution to this problem is nothing but simple application of Bragg's equation, which is n lambda is equal to 2d sin theta. Our aim is to now find out theta. So let us rearrange accordingly. Sin theta is equal to n into lambda divided by 2 into d. Substituting the values, n is equal to 1, lambda 0.154 nanometer divided by 2 into d. D is 0.415 nanometer. You can see here I have not converted nanometer into meter, because anyway here you have nanometer in both numerator and denominator, which gets cancelled, so no need of converting nanometer into meter. So if you simplify, we get sin theta is 0.1855, therefore theta is sin inverse of 0.1855, which is 10.7 degree. So what does it mean? Suppose you have a source of X-rays. Okay, source of X-rays, you have a crystal here. Now the X-ray just touches the surface of the crystal. Okay, just kisses the surface. So now the angle theta is equal to 0. Now if I either rotate the source of X-ray, or if I detect the crystal, okay, by using a mount table, and if I change the angle of diffraction, okay, I will slowly increase the angle of diffraction. When the angle between the source, that is incident beam, and the crystal is 10 degree, when the angle is 10 degree, we see a bright spot in the detector. And at what angle we are observing the bright spot? It is at 10.7 degree. So initially the X-ray source was at an angle 0 degree with respect to the crystal. Slowly you increase the angle from 0, 0.1, 0.2, 0.3. Nothing was observed in the detector. ಯಾಕಂದ್ರೆ ಈ ಎಲ್ಲ ಆಂಗಲ್ ಅಲ್ಲೂ ಬ್ರಾಗ್ಸ್ ಲಾ n lambda is equal to 2d sin theta satisfy ಆಗದಿರುವಂತ ಕಾರಣ we did not observe any bright spot. Okay, slowly you increase the angle 5 degree, 5.1, 5.2, nothing is observed. 7.1, 7.2, 7.3, nothing is observed. 9.5, 9.10. ಅದೇ ರೀತಿ angle 10.7 degree ಬಂದ ಕೂಡಲೇ the detector detects X-rays. So there is a bright spot observed in the detector. Why we are observing a bright spot? Because at this angle now, that is 10.7 degree, n lambda is equal to 2d sin theta equation is satisfied. That is the reason why you observe a bright spot. So the first diffraction spot is observed at 10.7 degree, therefore it corresponds to a first order reflection. Now what we do is we further increase the angle beyond 10.7 degree. When the angle now becomes 10.8 degree, immediately n lambda is equal to 2d sin theta is now not satisfied. So there is no bright spot at 10.8 degree. Further I will increase the angle, further I will increase the angle. At a particular angle theta, again a bright spot is observed. That angle is uh, also corresponding to Bragg's angle, but it corresponds to a second order reflection. The minimum most angle at which diffraction pattern is observed, that corresponds to the first order reflection. The next highest angle corresponding to maximum reflection will be called as second order reflection. Next angle is called as third order reflection, and so on. So the second part of the question is, after 10.7 degree, at what angle another diffraction spot will be observed? So the second part of the question is to find out the value of theta for second order reflection. Again, we have to use the Bragg's equation. M lambda is equal to 2d sin theta. So sin theta is equal to n lambda by 2d. All the values are given. However, here we have to substitute n is equal to 2 because it is now the second order reflection. 2 into lambda, that is 0.154 nanometer, divided by 2. This 2 is from the formula, okay, 2d. 2 into 0.415 nanometer, which works out to be 0.3711. Therefore theta is sine inverse of 0.3711. Okay, the angle answer is 21.8 degree. 21.8 degree. So after 10.7 degree, I will be rotating the either the X-ray source or the crystal. Okay, and when the angle between the source and the crystal reaches 21.8 degree, a second diffraction spot will be observed, and no spot will be observed between 10.7 degree and 21.8 degree. 10.7 degree one spot, in between nothing, all dark. When the angle reaches 21.8 degree, another spot will be observed, which is nothing but the second order reflection. Okay, so this is the uh, meaning of first order reflection and second order reflection, right? So I think these two problems are sufficient. Now let us focus a bit on application of Bragg's law. The important application of Bragg's law is the application of Bragg's law is determination of crystal structure. What do you mean by crystal structure? Determination of crystal structure. It means finding out what the crystal is made up of, that is the chemical constituent of the sample, and how the constituent particles of the crystals are arranged. Are they arranged in cubical way, or monoclinic crystal system, or triclinic crystal system? Is it a primitive cell, or is it a body centered, is it a face centered? Everything constitutes determination of crystal structure. Okay, so to understand the application of Bragg's law in determination of crystal structure, we have to go through some equations. Okay, all these equations can be derived by using geometry uh, in a crystal, but those derivations are not required here, so we will only consider some important equations that we require in studying the applications. Okay, so now we are discussing the distance between planes, interplanar distances in a crystal system. Suppose, let me draw a simple picture here. I have a unit cell here. In a crystal, I have a unit cell, and attached to it there is one more unit cell. You will remember, crystal is nothing but arrangement of unit cell in a systematic, regular, periodic, three-dimensional way or manner. Okay, so you have lot of unit cells. Okay, Still you have many unit cells in this direction, you have unit cells in this direction, you have unit cell in these directions, you have unit cell in all the directions. I have just drawn 2 unit cells. Okay, or let me draw one more unit cell, 3 unit cells. So let me consider this as y-axis, this as z-axis, and this is the x-axis. So what is the length of the unit cell along x-axis? The length of the unit cell along x-axis is A, length of the unit cell along y-axis is B, length of the unit cell along z-axis is C. Let us consider 100 unit cell. For example, 100 unit cell. Remember, in the last class we discussed 100 unit cell. A 100 unit cell means a sorry, I'm doing a mistake. It is not 100 unit cell, it's a 100 plane. 100 is nothing but the Miller indices HKL. H is equal to 0, sorry 1, K is equal to 0, L is equal to 0. So what do you mean by 100 plane? A 100 plane cuts the x-axis of each unit cell at a distance A from the origin and is parallel to y as well as z axis. So where do we have our 100 plane? In each unit cell we can recognize a 100 plane. So this is a 100 plane of the first unit cell. This is the 100 plane of the second unit cell. This is the 100 plane of the third unit cell. Similarly, this is also 100 plane of the unit cell which exists here. Okay, and so on. Now the question is, what is the distance between two neighboring units planes? So what is D100? Let me change the color. Okay. So what is D100? What do you mean by D100? It is the distance between two 100 planes. Remember, the distance between these two 100 planes is same as the distance between these two 100 planes. So the distance between two planes having same HKL values are always same, provided the planes should be adjacent to each other. So is there any systematic way of deriving a general formula to find out DHKL, that is, what is the distance between two neighboring planes whose Miller indices is HKL? The answer is yes, we can derive them. That's a very definite formula through which we can calculate DHKL. As I already told, we need not derive this equation, we will directly use the equation. Okay, the distance between two HKL planes depends on two things. Okay, it depends on two things. The distance between two HKL planes depends on the values of HKL. It depends on the values of cell parameters A, B and C. I repeat, the distance between two HKL planes depends on the values of HKL of that plane, and it also depends on the cell parameters A, B and C. How? Mathematically I have given here. Okay. First, for an orthogonal crystal system. You remember in our earlier video we discussed about 7 types of crystal system. What is an orthogonal crystal system? A system where A is not equal to B, not equal to C, but alpha is equal to beta is equal to gamma is equal to 90 degree. For such a system, the relation is given here. The relation is 1 divided by D, that is distance between HKL planes whole square, is equal to H, that is Miller index along x-axis, divided by A, that is length of the unit cell along x-axis whole square, plus K, again Miller index along y-axis, unit cell length along y-axis whole square, plus L, that is Miller index along z-axis, divided by C, that is unit cell along z-axis whole square. Okay, whole square. So this is the formula to calculate DHKL for an orthogonal crystal system. For a cubic system, what do you mean by cubic system? For a cubic system, all unit cell lengths are equal to each other. That is, A is equal to B is equal to C, and alpha, beta, gamma all are equal to 90 degree. In such system, DHKL is given by a very simple formula. A, that is the unit cell length, divided by square root of h square plus k square plus L square. See here in the formula we have only A. We have only A. We don't have B and C because A is equal to B is equal to C. So we have a very simple formula for a cubical system. And please remember this formula because this formula will be used in our next discussion about cubic system. If the system is tetragonal, for which A is equal to B not equal to C, alpha, beta, gamma all are equal to 90 degree, the relation is 1 over d HKL whole square is equal to h square plus k square whole divided by a square plus L square divided by c square. Okay, please remember this formula, very easy to remember also. So these three formula tells us how to find out the distance between two HKL planes in a orthogonal system, cubical system and tetragonal system. Similarly, you can derive formula for other crystal systems, but they are very difficult to derive, not easy as these three systems. Okay. Another discussion that we have to have is the interplanar distance in a cubic system. Specifically, our focus is on three important planes: 100 planes, 110 plane, and 111 plane. Okay. What do you mean by 100 plane? 100 plane is a plane that cuts x-axis at unit cell length and is parallel to y and z axis. So this is 110 plane. Sorry, 100 plane. What is 110 plane? A 110 plane cuts x-axis at A, y-axis at B, but is parallel to z-axis. So how do we visualize this plane? So this is x-axis, this is y-axis, this is y-axis, and this is z-axis. So a 110 plane should cut x-axis at A, y-axis at B, and parallel to z-axis. So this diagonal plane is the 110 plane. What is 111 plane? A 111 plane cuts x-axis at A, y-axis at B, and z-axis at C. It cuts all the three axes. How does it look? Something like this. This is a 111 plane. So what we are discussing now is what is the distance between two 100 planes. Similarly, what is the distance between the successive 110 plane and the distance between successive D11 plane, 111 plane in a cubic system. Okay, again we are directly discussing the result without going into derivations. In a cubic system, you can have three types of Bravais lattice: a simple cubic, where particles are present only in corners; face-centered cubic, where particles are present in 8 corners and also on the center of 6 faces; a body-centered cubic, where particles are present in corner and at the center of the unit cell. So the ratio of D100 is to D110 is to D11. Andreno, I will find out the distance between 100 plane in a cubic system, D110 plane, and I will also find out D111 plane and take the ratio. And it is observed that if the system is a simple cube, then the ratio is A is to A by root 2 is to A divided by root 3, where what is A? A is the unit cell length. So D100 is to D110 is to D111 in a simple cube is A is to A by root 2 is to A by root 3. Since A is common in all the ratio, we can cancel them. So it is nothing but 1 is to 1 by root 2 is to 1 by root 3. If you simplify, it is 1 is to 0.707 is to 0.577. So you have to remember some numbers. If it is a simple cubic system, then the ratios of the distance between 100, 110 and 111 plane is given by this. Suppose if it is a face-centered cubic, then the ratio D100 is to D110 is to D111 is given by A by 2 is to A by 2 root 2 is to A by root 3. Again, if we cancel this common term A and simplify, it is 1 is to 0.707 is to 1.154. And finally, in the body-centered cubic, the ratio of the three distances is A by 2 is to A by root 2 is to A by 2 root 3, which works out as 1 is to 1.1414 is to 0.577. So what importance this information contain or has? Suppose if in an experiment I am able to find out the distance D100, D110, D11 and take the ratio, then it is possible to find out the lattice. For example, I will take a crystal and perform the X-ray diffraction experiment, find out three distances D100, D110 and D11 and also find the ratio. If the ratio is 1 is to 0.707 is to 1.154, if the ratio is very close to 1 is to 0.707 is to 1.154, what does it mean? It means that the given crystal system belongs to face-centered cubic lattice. Suppose ನಮ್ಗೆ ಕೊಟ್ಟಿರುವಂತಹ sample X-ray diffraction experimentally, okay, then I will conduct the diffraction experiment and find out the ratio D100 is to D110 is to D11, and if this ratio is 1 is to 0.404 is to 0.573, we can see that this ratio is very close to a body centered cubic lattice. So ಇದರಿಂದ ನಾವು ಏನಂತ ಜಡ್ಜ್ ಮಾಡಬಹುದು, the given crystal belongs to body centered cubic. Okay, so these ratios are very important uh, numbers related to the respective lattice. So by finding out this ratio, it is possible to predict what is the lattice, whether it is simple cubic, body centered cubic or face centered cubic. Okay, so all these are chunk of information that we are borrowing from here and there. Okay, ಸ್ವಲ್ಪ ಡಿಸ್ಕಂಟಿನ್ಯೂಸ್ ಆಗಿರ್ತದೆ, ಕಂಟಿನ್ಯೂಸ್ ಇರಲ್ಲ ಈ ಎಲ್ಲ ಡಿಸ್ಕಷನ್. Let me end today's video with an important note which will be useful in the next video. According to Bragg's law, n lambda is equal to 2d sin theta. Let me rearrange. Then d is equal to n lambda by 2 into 1 by sin theta. For a given order of reflection, n is fixed. Suppose if it is first order, n is always 1. If it is second order, n is always 2. So for a given order of reflection, n is fixed. And during an experiment, wavelength of X-ray is always fixed. We do not change the wavelength in middle of the experiment. So lambda is also fixed. Anyhow, 2 is constant. So this n into lambda by 2 is a constant. So what we can write is, therefore d is proportional to 1 by sine theta, or the distance between 100 plane should be proportional to 1 by sine the sine theta 100. What is theta 100? It is the Bragg's angle for the reflection of X-rays from a 100 plane. Similarly, we can write d110 is should be proportional to 1 by sine theta 110. What is theta 110? It is the Bragg's angle corresponding to the reflection of X-rays from 110 plane corresponding to maximum reflection. Similarly, d111 should be proportional to 1 by sine theta 111. Theta 111 is the Bragg's angle corresponding to maximum reflection of X-rays from a 111 plane. So if we take the ratio, we get d100 is to d110 is to d11 is same as 1 by sine theta 100 is to 1 by sine theta 110 is to 1 by sine theta 111. Okay, instead of d100 here, since it is proportional to 1 by sine theta, I have written as 1 by sine theta 00. ಅದೇ ರೀತಿ d110, instead of that we have substituted 1 by sine theta 110. ಅದೇ ರೀತಿ d111 ಬದಲು 1 by sine theta 111, because they are directly proportional to each other. So the ratio of the interplanar distance is equal to the ratio of 1 by sine theta. I repeat, the ratio of the interplanar distance is same as the ratio of 1 by sine theta corresponding to the same plane. So with this some information, what we will do in the next video is we apply Bragg's law to determine the structure of sodium chloride and potassium chloride. With this note, I conclude this video. Thank you.